Department of Electronics and Communication Engineering, National Institute of Technology, Silchar. He earned his BTech and MTech degree in Radio Physics and Electronics from University of Calcutta in 2002 and 2004. He received his PhD degree in Department in Electronics and Communication Engineering from IIT Kharagpur. He is a senior member of IEEE, Fellow of IE, and Fellow of IETE. His area of interest are wireless communication, wireless networks, UAV-based wireless communication, and wireless sensor network. So he has a lot of credential to having 82 renowned publications. He has taught several courses at NIT Silchar on wireless communication, electromagnetic field theory, and he has guided several students also, including 13 PhD students, 12 postgraduate students, and published several book chapter, patent, and conference proceedings as well. So I welcome Professor Hoshian to this particular FDP on 5G and beyond wireless communication. Over to you, sir. You can share your slides
Okay,
and
thank
start
you,
with
Dr.
the
Nanda and Dr. Ravi, for your invitation. Let me just share my screen.
Yes, sir.
Is it visible?
Yes.
Okay.
Just make it full screen and
Uh-huh.
then you can start.
Okay, can I stop my video or so that bandwidth or that will be
Yes, but no problem from our side.
okay, okay.
You
So
can
If
keep it on also. There is
bandwidth is
no
an
okay,
issue
okay,
for
okay.
you, you
problem.
can switch it off.
Okay. Huh?
If bandwidth is an issue for you, then you can switch it off.
For us,
Okay.
there is no problem.
Okay. I think it is visible and scrolling now means
Yes, yes,
Yes.
yes. It is
okay.
visible and
Full
perfect.
screen. Yes, perfect.
Yes.
Please continue.
Okay. Thank you. Good afternoon to all the participants. I am Dr. Ashraf Hossain. I shall be talking on millimeter wave communication and UAV based wireless communications. So the presentation is organized like that. I shall talk about the wireless history, then the current and next generation wireless systems. What are the technical challenges for the current scenarios? And in that context, the 5G, which I'll talk about, then the how to fulfill the requirement of the 5G, then the millimeter wave, the essential, the requirement of the millimeter wave will be discussed, and then the challenges and the prospects of the millimeter wave will be discussed. And after that, we shall talk about the wireless communications above 100 gigahertz. Then I shall talk about the UAV based wireless communications. So if you talk about the wireless history, so earlier in the ancient time, the communication takes place. Communication, that means that that time it was the non-electrical form. At that time, then the communication or the exchanging of information was done by some non-electrical method, like the smoke signals or the carrier pigeons to carry the some message from one place to another place. But these are all non-electrical format. Then the later on the this electrical signal or electrical version of the communication started by Marconi in 1880s, and after that there are many sophisticated communication devices have been developed, and during the World War II it was a lot of applications were developed. And presently, the cellular communication, the 1G, 2G, 3G, 4G, 5G, the growth of the users are exponential. And here the voice, data, multimedia, ubiquitous communications are there, and all the developed country, third world country, developing country, all everywhere the traffic, wireless traffic is growing exponentially. Now, if you talk about the statistics, now population of the globe is around 8.2 billion, and out of that, India has 1.46 billion, and out of that, now 5.78 billion, that means 1 billion means 100 crores. So 5.78 billion users use the mobile phone, and out of that 87% are smartphone, and smartphone means they are also using the internet. And overall global population, around 70% use the internet. So there is a huge demand of the high data rate, and that's why the evolution from one generation to another generation, like 3G to 4G, 4G to 5G, takes place. And future wireless network will be like that, everywhere, wherever is the people, wherever is the device, they will be interconnected to each other. And that's why the smart cities, smart home, autonomous cars, body area network, Internet of Things, all these are the different sorts of communication. Now, what are the challenges in order to provide this kind of communication? There are many challenges are there. So one challenge is like the network or radio challenges. Now the data rate requirement is in the order of gigabits per second and no error. So how to, it is very difficult to provide high data rate with the almost no error. Similarly, the energy efficiency, all the communication devices, processor, they consume energy. So energy consumption should be minimum. As a result of that, the green communication uh, has been evolved. In communication, one of the important resources is the spectrum. So spectrum is limited. As the communication engineer, the task is to use the spectrum, available limited spectrum, for developing the system. And also the, in order to provide the communication for the devices, communication for the man, communication for the everywhere, that that should be reliable, and the coverage is very much important. Now for cellular system, if base station is there, that can provide the coverage, but there are several issues that coverage holes are there. So that's why there are many technologies are there for provide the high coverage. And also almost there are heterogeneous types of networks like the ad hoc network, LTE, 4G, 5G, Wi-Fi, all kinds of networks are there. So the challenges are there to integrate or the work over all kind of networks, and as a result of that the inter-network handoff is also required. So this is the challenges for radio point of view. Another challenges are there, that is from the device or system on chips kind of thing. So on the system of chips, many processors have to be implemented, then the complexity, performance, of course the size, power, cost, all are crucial things for designing the processors or system chips like that. And then these devices must be working in the high frequency, because in order to provide the high data rate, the millimeter wave or high frequencies are essential. And of course they are working in on the arrays of antennas, so multiple antenna has to be integrated. And so these are the challenges which we are currently facing. And the requirement, that is actually I already mentioned, that the growing traffic and devices. So in this figure that is shown the data traffic used per month by the users, and this is taken from the Cisco. This data is up to 2018, but the rate of that is growing rate is exponentially, it is increasing. And this is up to 2023, that is also global internet users. It is going on around 5.3 billion users are using the internet. And this is the updated one from 2005 to 2025. here the number of internet users in billions, and this is the percentage of population. So around 70% of the global population they use the internet. So the high demand for high data rate and the high volume of the data are used by the users across the globe. And in this figure, the y-axis that shows the traffic terabyte per month, and the x-axis that is shown as the year. So that is taken from the C-scope. So actually, that was the some projection, and then the actual. So it is here it is shown that the video data, there are three types of data that they are: video data and the machine to machine communication, so and file sharing. So out of these four, in the coming year or presently, the demand for the video traffic is more, and that dominates over the data and the machine type communication. So that's why from the 4G to 5G, already 5G has been installed in our country, and so the what are the requirements for the 5G and targets? The 5G targets were higher system capacity. And then the latency for the 5G should be lower than the 1 millisecond. Energy saving and cost reduction for the energy saving for network and terminals, and then the reduced network cost, including backhaul. Then the massive device connectivity. In 5G, the large number of devices are they will be must be connected, and in the even in the crowded areas, and of course the higher data rate of the order of Gbps rate. So how to fulfill this? So in order to fulfill the high data rate, the one of the important thing that is required is the bandwidth. So whatever is the existing cellular service, the bandwidth, whatever spectrum was used, that was limited to 2.1 gigahertz. But in order to provide the high data rate requirement for the 5G network, that of the order of gigabits per second data rate, that can be possible through the millimeter wave. And then the millimeter wave and the heterogeneous networks, that is the head nets, are some possibilities are there. Head nets plus massive MIMOs are there. Millimeter wave and massive MIMO are there. So these are the different combinations, and are there. So in this context, the heterogeneous networks, that is a critical architecture that combines different cell types and technologies such as macro cells, small cells like pico cell and femto cell, and Wi-Fi to create a single unified network. So the head nets, that advantage is that network capacity will be improved, coverage at the same time spectral efficiency all will be improved, while lowering power consumption to meet 5G's demand for high data rates and reliability. But there are some challenges in the 5G head nets. That are the those are the interferences, and then optimizing resource allocation and ensuring seamless user mobility, which are being addressed with techniques like machine learning and cloud-based platforms. This is actually some plot is shown as the along the y-axis data rate is shown in the, and the x-axis is the device density, devices number of devices per square kilometer area. So here different zones are shown: R1, R2, R3, R4, R5. So R4 is the low data rate and the low density. So where thing is that data rate is low and the device density is low, but here the ultra reliable connectivity can be provided. Whereas the R3 is low data rate or moderate data rate, and the device density is very high. So that is massive access for sensors and machines. Whereas R1, R2 are almost high data rate but density is low. And R5 is the one where the data rate is also very high, at the same time that um, device density is also very high. So the challenges is to in this area. So reliability and the latency are the another requirement for the 5G. So in order to provide that, in order to obtain this new radio access technology, RAT is required, and in that context, the phantom cell, one of the concept that was used, where the a big area, that is the macro cell, usually the size is more, and that is divided into small regions, and usually the lower frequency bands, like those are given assigned to the macro cells, and under the macro cells some phantom cells are there with smaller area, and they are higher frequency bands will be given, and splitting of the control and user plane, that can, by introducing this phantom cell concept, the high data rate can be achieved. So phantom cell is that a macro cell acts as a master and manages the phantom cells, which are small cell deployed within its coverage area. And so phantom cells often use higher frequency bands to achieve higher data rates, while the macro cell use a lower frequency. And this setup enhances network capacity, especially in high traffic areas, by splitting the control plane, CPL plane, and user plane, and for uploading data traffic from the macro cell to the phantom cell. In the crowded area where the macro cell is overloaded, in that case, that traffic from the macro cell can be transferred to the phantom cell. Now, this figure shows that the data rate for the different generation of wireless communication, not the 1G, 2G are shown here because they are very low speed. So 3G, 4G, 5G, three generations are shown here with the year of introduction, and two types of data are shown. One is the peak theoretical peak and data rate, and the that is the one that is the theoretically possible data rate, and that another data rate is that the first commercially deployed system that provides how much data rate. So in case of 3G, around 2000 to 2007, the peak theoretical data rate was 14 Mbps, whereas the achievable data rate for the first product was 384 kbps. And 4G, the theoretical data rate was 1 Gbps, and for the first commercial product that provides a data rate of 75 Mbps. And 4G was introduced in the year 2010, whereas 5G was introduced in the year 18, and the theoretical data rate was 50 Gbps, and whereas the first commercial product that gave the data rate of 6 Gbps. So this is the variation from the theoretical and the practical data rate, but that tells this figure that from 4G to 5G, data rate enhancement is around 50 times. So how to fulfill, how to achieve this high data rate for the 5G, so that millimeter wave spectrum is needed to meet the 5G demand. And now where the millimeter band exists in the spectrum, that is very much important thing. If this is the spectrum that is governed by the Federal Communication Commission. So here the different bands are shown for the different communication or broadcasting system. AM radio is shown here, that is in the range of 550 kilohertz to 1600 kilohertz. Then the TV broadcast takes place over these two bands. FM radio is here. So FM band is, we know that the 88 to 108 megahertz. So TV broadcast takes place before that, around 60 megahertz. Sorry, another band around 300 400 megahertz for TV broadcast. And the cellular, earlier cellular means cellular up to 4G, that was 800 900 megahertz one band, another band around 2000 megahertz, 2200 2100 megahertz band. And this is the Wi-Fi band, 2450 megahertz, 2.45 gigahertz Wi-Fi band. And this is the then the come for the millimeter wave, that is 60 gigahertz spectrum, around 5 gigahertz or 7 gigahertz bandwidth is available here, and 77 gigahertz vehicular radars are also there. So now 5, so millimeter wave that resides over this region, that with the wavelength is from 1 millimeter to 10 millimeter, and frequency range is 30 gigahertz to 300 gigahertz, that lies over here. And but millimeter, before using millimeter wave in the 5G, earlier the that millimeter wave like 60 gigahertz was used for some other works. Similarly, 77 gigahertz was used for the vehicular radar. So, but there are several challenges are also there in the 60 gigahertz, that is used for high speed, short range wireless communication, including wireless internet and data transfer. This band offers multi-gigabit speeds, security, and is unlicensed. That means this no need to buy this, no need to purchase this spectrum. It is unlicensed. And there are many applications of theirs for 60 gigahertz applications, that actually that from the earlier application and the present day applications, wireless HDMI, that is used for high bandwidth, low latency audio and video transmission between the devices. And similarly, the WIGIG standard that adds 60 gigahertz connectivity to Wi-Fi for faster data transfer, especially for short distances. And also the wireless backhaul has been developed that provides a quick and cost-effective alternative to laying fiber optic cables for connecting cell towers or other network infrastructure. High resolution wireless display enables compressed high definition video streaming. And also the sensor, the technology is also used in small compact radar sensors for applications like security and presence detection. This shows that the wireless backhaul, which is used for base station to base station connection by using the millimeter wave. But the challenge is that the range is not more than maybe within 200 meter, 500 meter, less than 1 kilometer. But there are some solutions are there by using the beamforming, or that range can be extended. Another applications were there, 77 gigahertz radar. So that radar was earlier also used before using the 5G. And that 77 gigahertz radar has some advantages, that gives the high resolution, and that allows for greater resolution. That means smaller objects can be detected and their shapes can be better resolved. And the size 77 gigahertz, so it is in the millimeter, on the wavelength size of the order of millimeter. So the antenna size, the compact size that provides, so the short wavelength enables the use of smaller antennas which are easier to integrate into a vehicle. And because of the 77 gigahertz, so bandwidth is quite high, very high, so bandwidth enables high range resolution. Then wide availability. This frequency band is widely available for automotive applications, with regulations supporting its use in many regions. But the range is only 250 meters, even in the low visibility condition. So these shows that the mobile and vehicle connectivity. Uh, the millimeter wave spectrum, that is here the spectrum is divided into two part. One is the centimeter wave, another is the millimeter wave. So from below 30 gigahertz and above 30 gigahertz. So above 30 gigahertz is the millimeter wave, below 30 gigahertz is the centimeter wave. So the whole bandwidth in the centimeter wave is less than 1 gigahertz, and there are several bands are there. 5.2 gigahertz with a bandwidth of 550 megahertz. Then 2.4 gigahertz, which is used for the Wi-Fi, so 100 megahertz bandwidth is there. 900 megahertz band carrier is there, where 2.6 megahertz bandwidth are used. And 28 gigahertz, where 1.3 gigahertz bandwidth is there, but total bandwidth is less than 1 gigahertz. But whereas in the millimeter waves, that starts from 30 gigahertz to 300 gigahertz, but over the 30 to less than 100 gigahertz, over the range of 30 gigahertz to 100 gigahertz, there are several bands are there. 39 gigahertz, where bandwidth of 1.4 gigahertz available. 37 and 42 gigahertz, where 2.1 gigahertz bandwidth is available. Similarly, the 60 gigahertz where 7 gigahertz is bandwidth is available, and so in the millimeter wave there are 20 gigahertz bandwidth are available, and this is already mentioned. This is unlicensed. So up to 30 gigahertz to up to 100 gigahertz within this range, 20 gigahertz use bandwidth are available, and that can be used. But there are many challenges are also there, which I'll talk about later on. So more spectrum in bands not previously used for the cellular. So this band was not used for the cellular. Cellular was only up to 900 megahertz in the 2.1 gigahertz. So in the 5G, the millimeter wave is going to use. Now, there are millimeter wave spectrum implications of millimeter wave spectrum, that cognitive radio for shared spectrum with satellite or radar, and this propagation, because the millimeter wave the propagation models are different. The signals are getting blocked. Blockage is one problem. Shadowing, millimeter wave signal cannot penetrate walls. Okay, so the radio propagation model will be different for the millimeter wave. And in the 5G scenario, 5G has the application that autonomous robots, the smart homes, smart cities, vehicle to vehicle communication, vehicle to infrastructure, vehicle to everything. So applications are there. This is just shown that the how antenna radiate, the array of antennas are used for directing the beam towards a particular direction. This is the now one problem of the millimeter wave is that blockage. So blockage is a major channel impairment. One problem is there in the millimeter wave, that is the blockage. So here in this figure, say one mobile handset is shown here. This is the same base station for this system. So this user and this base station is line of sight communication. Whereas between this and this, one building is there. So that is obstructed by the building. So non-line of sight communication. But in the millimeter wave, that signal is blocked by this building. Okay, so that signal will be blocked by this building. What is not applicable in the case of cellular communication, where the reflected signal will be there, but here it is blocked by the building. Similarly, a man can also block the 5 millimeter wave signal. Like this, here is a one base station. The signal is transmitted directly towards this direction. A man is here, then this handset will not get the signal because of this presence of the man. So blockage due to the people, blockage due to the building, even hand blocking is also there. This thumb is this antenna array is covered by the thumb or the hand, so that will be blocked. The signal will be blocked. So another cell body blocking also there. So I need models for blockage and system analysis for the millimeter wave spectrum, millimeter wave signal. Now the implications of blockage is that blockage properties for the millimeter wave that gives the challenges, but it has only one advantage, that interference will be less in one case. Means some interfere that will be also blocked, so some kind of interfere will be less. Say inside a building user is there, but that user will be blocked. Okay, so and that will not be getting the signal inside the building. Here it is shown that antenna lower array blocked by the person and upper array blocked by the fingers. Here and user has two, in the mobile handset has two array, mobile antenna array, top and the bottom. Top is blocked by the finger, whereas the lower array is open, that is not covered, but that is blocked by the human being. So blockage reduce the interference will be less, because the some unwanted signal will be blocked by the other obstacles. Now, how to mitigate that blockage in the 5G? So there are some methods are there that will mitigate the blockage. So spatial diversity, the network can establish multiple connections from device to the different base stations, so that if one is blocked, then second alternative path will be automatically link will be working. Then similarly, intelligent antenna systems, advanced antenna can adjust their beams to find an alternative path or compensate for signal loss, although this cannot fully overcome several blockages. In network planners use advanced models to predict potential blockages and strategically place base stations to ensure better spatial diversity and coverage, especially in urban areas. Reflective paths, in some cases, the signal can bounce off other surfaces to reach the device, creating a reflective path combination. Then dynamic point selection, a technique where a user maintains simultaneous links to multiple transmission and reception points to improve coverage and reduce latency caused by blockage. Now, another challenge is regarding the power consumption in the millimeter wave. So, this is the block diagram for the receiver side, where and that is actually designed for the below millimeter band. Okay, so actually, and the same the same structure if we use for the millimeter wave, say around 60 gigahertz and 1 gigahertz bandwidth, antenna, low noise amplifier, then RF chain, A to D converter, then the baseband processing. So this type of array means are there for say 4 antennas, 8 antennas, 10, 16 antennas are there. So and power consumption for the 60 gigahertz in the millimeter wave, that is for low noise amplifier, that consumes around 20 milliwatt, whereas RF chain consumes around 40 milliwatt, and A to D converter that consumes 200 to 350 milliwatt. So in a single chain that will consume around 300 milliwatt. So 300 to 400 milliwatt power will be consumed by a single chain from the antenna, low noise amplifier, RF chain, A to D converter. And if there are four such chains are there, then in the 60 gigahertz in the millimeter wave, it will be power consumption will be 2 watt, and that is very high. Whereas if we compare for the 2.4 gigahertz, this consumption for the 4 antenna will be around 120 milliwatt. So whatever is the existing circuit for the 2 gigahertz or 1 gigahertz range, that can, if we use the same circuitry for the millimeter wave, then the power consumption will be very high. So alternative millimeter wave MIMO architecture are needed for the to overcome the problem of over power consumption. And for that, the RF combining or baseband combining are used, where whatever is the receiving number of antennas, after RF combining, the number of RF chain is lower than the number of receiving antennas, and similarly the ADC will also be reduced. As a result of that, the overall power consumption has been reduced, and that has been mm, achieved through the signal processing. So RF combining, that is the process of merging two or more radio frequency signals into a single output using a passive device called the combiner or power splitter. So by using the power splitter, the number of RF chain can be reduced. And these devices are crucial for applications like connecting multiple antennas to a single radio or linking multiple radios to one antenna, and they are designed to combine signals with minimal loss and signal degradation. They are essential for increasing power or managing signal flow in wireless systems, and can be used to combine signals on the same frequency band, while a multiplexer is used for combining signals in different frequency bands. Yes, so in order to overcome the high path loss in millimeter wave, one solution is that massive MIMO, multi-user or massive MIMO at millimeter wave is used for beamforming, or to direct the radiated beam towards a particular user that concept, like 256 antennas or more antennas are there in the base station, and from base station to that radiates the signal to a particular user by the method of beamforming, and large arrays are natural application of massive MIMO techniques. So massive MIMO uses many antennas. Unlike traditional MIMO systems with only a few antennas, massive MIMO base station have large arrays of antennas that creates focused beams. These antennas arrays are used to create multiple highly focused signal beams that are sent directly to individual user. And this is called the beamforming. That boost capacity and speed. And individual speed may be up to 10 Gbps can be provided by this kind of massive MIMO. And that because the beams are highly directed, highly directional and narrow, so that will reduce the interference, and that also improves the signal strength, and as a result of that, the high speed and high data rate that can be, which is the essential requirement of the 5G, are achieved by this method. So already another method, hybrid combining is used for this improving the performance improvement. Now the millimeter wave, we need to mention that first millimeter wave experiment was performed in India around 100 years ago. Sir Jagdish Chandra Bose from India, he from Kolkata, he did his experiment in the 60 gigahertz band. He designed the transmitter, he designed the receiver, and he was able to send the signal over a short distance from one room to adjacent room. No, millimeter wave band, there are many applications, Bose experiments in the 1895, then the fire control radar in the 1944, radio astronomy around 1970, automotive radar, satellite-based remote sensing, satellite links are there in the some millimeter bands. You know, the Ka band that is near about in the vicinity of the around 26 to 40 gigahertz, that Ka band that is in the millimeter wave band. Then wireless backhaul is there, wireless HD is there, Wi-Fi that is also used in the millimeter wave. You know, if we look at the spectrum for the 60 gigahertz, how it is allocated all over the globe, around 7 gigahertz bandwidth is allotted for everywhere, North America, Europe. So, and from around 56, 57 to 66 gigahertz, over the 7 gigahertz bandwidth are allocated to normal 5 gigahertz common bandwidth among several countries. And this is unlicensed. Now, one of the challenges of the millimeter wave is that uh, attenuation. The signal gets attenuated because the wavelength of the order of millimeter, and when signal gets propagated through through the atmosphere or through the air, air particles, that size of the air particles are also near about the same with the wavelength of the millimeter wave, and there is a scattering absorption of the signals take place, and as a result of that, high attenuations are there. So at 60 gigahertz, so in this figure, y-axis sea level attenuation, that is unit dB per kilometer, and x-axis the frequency is shown in gigahertz. So there are high peaks are there. One peak is at present at 60 gigahertz. So the 60 gigahertz, where the attenuation level is 20 dB per kilometer, and this is due to the atmospheric oxygen. Whatever is the oxygen, we know that the atmosphere contains the 80% of the oxygen. So due to presence of the oxygen particles, oxygen gas, the millimeter wave signal at 60 gigahertz gets absorbed. Okay, so high attenuation takes place at 60 gigahertz. 20 dB per kilometer means 1 kilometer distance if it travels signal, then the signal strength will be reduced by 100 times. So this is a huge loss, huge attenuation. of the signal. Similarly, 120 gigahertz is another band is there, but the intensity of the attenuation is maximum for the 60 gigahertz. Similarly, the water vapor that contains in the atmosphere, because of that, absorption takes place around 23 gigahertz. So in this figure, near about 20, and here one peak is there. So that due to the water vapor. Similarly, 180 gigahertz, another band, another peak is there, where also the attenuation takes place because of the water vapor presence in the atmosphere. So these are the challenges that if we use the particularly 60 gigahertz, then because of the atmospheric attenuation is there. Similarly, the rain has also the effect on the signal. We have noticed, everybody has noticed that during the watching the television from the DTH service direct to home, because the signal comes from the satellite, and if heavy rains are there, if proper mechanism are not taken, that sometimes the signal gets attenuated, signal lost are there. And so rain attenuation at 70 gigahertz band, heavy rain, 25 millimeter per hour, the rate is around 10 dB per kilometer. And as a result of that, the high attenuation, that cell size will be reduced to 200 meters. This is shown that the millimeter wave, that 5 millimeters and 16 antennas integrated circuit are shown here. That shows a compact design of the antenna system. So key challenges are in the millimeter wave, that the range is the key challenge. So range is very small. How to increase the range? And free space propagation law, that is the received power at a distance r, when the transmit power is pt, that is given by gt gr, that is gt is the transmitting antenna gain, gr is the transmitting antenna receiving antenna gain, gr, lambda is wavelength, and r is the distance. So free space channel gain, that is proportional to the lambda square, but antenna gains, that is inversely proportional to the lambda square. So path loss, huge path loss are there, but by the advancement of the signal processing, antenna design, beamforming, that path loss can be overcome. Also, the problem of shadowing, and that significant transmission losses are there in brick or any concrete, that will also create the attenuation shadowing effect of around 35 dB. Even human body also, up to 35 dB signal loss are there. Similarly, from the surrounding environment, foliage, the large trees, that also affect the signal strength. That results is taken from the author, that D.L. Jones and R.H. Espland, and the Violet. And they have from their result, it is found that the attenuation due to foliage increases at millimeter wave frequencies. However, the spatial variation in shadowing is greater than lower frequencies. Millimeter wave frequencies have very small wavelengths, hence smaller Fresnel zone. Wind also affect the link quality, and this received signal level at frequency 9.6 gigahertz to 28 gigahertz, 57 gigahertz, 96 gigahertz are performed, and that is for every cases. These are the comments are obtained. And another thing that is also valid for the millimeter wave, that the LMDS performance, that local multi-point distributions service, LMDS. Here the table that shows for different antenna height, and this column is shown that signal is not available. So antenna height for 11.3 meter, and measurement is taken for surrounding all the area around from the antenna, that 32% area are uncovered. Whereas if we decrease the antenna height, then this area is more, means the uncovered area is increasing by decreasing the antenna height, or in other words, we can tell that the antenna, by increasing the antenna height, the coverage area is increased. So that is the from general intuition we can tell that. And Seidel and Arnold measured signal strength up to 5 km for wireless backhaul at 28 gigahertz. Coverage area increases with receiver antenna height. Receiver antenna scanned only azimuth direction, and study showed elevation angle scanning increases coverage significantly. And this is the channel path loss for the 73.5 gigahertz bandwidth carrier frequency. This was done by, it is taken from the reference of T.S. Rappaport, that path loss and the transmitter receiver separation are measured. So here maximum separation is shown from 1 meter to 200 meter, and over that around 140 dB path loss takes place. So that path loss is used. So measurement is shows that line of sight measurement and non line of sight measurement are taken place, and from that curve fitting algorithm, and the path loss exponent has been calculated, and then the standard deviation, if we follow the log normal shadowing path loss model, and then the sigma is there, sigma for line of sight, sigma for non line of sight, are calculated. This shows the propagation path loss exponent for different so maximum coverage distance in the y-axis, x-axis combined transmitter receiver antenna gain, and it is found that for different path loss exponents, say n equal to 3, n equal to 4, n equal to 5, different distance can be covered. When the path loss exponent is 3, maximum coverage distance can be 700 meter for combined transmitter receiving antenna of 20 dBi. And similarly for path loss exponent n equal to 5, then the distance may be coverage distance up to 350 meter, whereas combined transmitter receiver antenna gain is for 24.5 dBi antenna. So next, the radio channel measurements, we have taken that sliding correlator hardware, and that was actually this was designed by Rappaport et al. And we have shown here that sliding correlator transmitter, and this is for the sliding correlator receiver. I am not going to the details of that. Again, the path loss is shown for different transmitter receiver separation, and here the different environment the measurement has been taken. Path loss is increasing with the separation between transmitter receiver, and clear line of sight, LOS partially obstructed, non line of sight. Different measurements are taken, and then it is found that the path loss exponent in the clear line of sight it is 1.89, and in other case the LOS all 2.30, non line of sight it is obtained as 3.82. Of course, this measurement, this result is that was measured by Rappaport et al. In the USA, so that depends on the environment surroundings. So same kind of thing is there for 38 gigahertz cellular path loss is measured, and that is path loss is plotted for the different transmitter receiver separation. Now let me explain the now in spite of the high path loss present in the millimeter wave, now how to increase the range of the communication link, how to increase the separation between the transmitter and the receiver distance. So beamforming in 5G is one of the essential thing that enhances the spectral efficiency as well as the energy efficiency. So MIMO system, that RF chain for each antenna is not feasible in the millimeter wave, and so beamforming is a technique that uses. So let me explain the beamforming, a technique that uses multiple antennas to focus radio signals into a concentrated beam directed at a specific user instead of broadcasting them in all directions. This focused approach improves efficiency, reduces interference, increases network capacity, and enhances signal strength, which is crucial for the millimeter wave in 5G network. often used in conjunction with massive MIMO to allow base stations to manage multiple simultaneous data streams to different users. Now, how to achieve this beamforming? That how does it work? That direct by using the directional transmission. So instead of broadcasting a signal in 360-degree omnidirectional pattern, 5G base station uses its antenna array to create focused beam. So by creating the focused beam, that will be focused to a particular direction. And so, signal manipulation, the technique manipulates the phase and amplitude of the signal sent from each antenna to create constructive and destructive interference patterns. And this steers the signal in the direction of the intended receiver. So, only the intended receiver will receive the signal. As a result of that, interference will be reduced by the process of beamforming. And massive MIMO, that beamforming is a key component of massive MIMO, so which uses a large number of antennas at the base station to transmit multiple independent data streams to different users simultaneously. And benefits of the beamforming already mentioned are again that improved network capacity, more users can be served at the same time because signals are not interfering with each other as much. Higher data rate, focusing the signal increases its strength, leading to faster and more reliable data transfer. Reduced interference because the beams are very directed. Better signal quality is also obtained. Increased energy efficiency, effective use of high frequencies, and this is taken place in the millimeter wave and high bandwidth. So as a result of that, that is high data rate is achievable. But the millimeter wave, which has a short range and are easily blocked by the objects. Now, one option to increase the range, that is by using the relay. So significantly that relay network for the cellular system was used, but that was the gain was not very significant because the cellular system is bandwidth limited, whereas the millimeter wave is noise limited. So some study, some work, researchers can pursue their research by using the multi-hop relay at millimeter wave. The range can be extended, but at the cost of the delay will be more. So far we have discussed about the millimeter wave below 100 gigahertz, their challenges, characteristics. We have discussed the blockage of the millimeter wave. Then we have discussed that beamforming, the attenuation or the atmospheric condition. Now, what are the applications of the wireless communication? How it can be extended beyond the 100 gigahertz? Uh, so that we shall now discuss. Again, the electromagnetic spectrum is shown here, and it has different applications are shown here. Say broadcast radio, television, already discussed cell phone in this band. And so beyond 100 gigahertz means that is the terahertz or millimeter wave, and the terahertz signals are there. This is again shows the evolution of wireless technologies. So 1933 FM radio, then fast handheld phone, Wi-Fi in the year 2003, 2.4 and 5 gigahertz, 2019 that foldable smartphone, humidity is shown, rain. Now in the millimeter wave and terahertz application, so that there are many applications are there when wireless cognition, so robotic control or drone fleet control, then sensing are there. Sensing has the important application for measuring the quality of air. And then personal health monitoring system, gesture detection and touchless smartphones, explosive detection and gas sensing. Yes. So imaging is another application where see in the dark by using the millimeter wave camera, high definition video resolution radar, terahertz security body scan. And of course, the communication where the wireless fiber for backhaul is there, and that replaces the fiber optics backhaul. And then intra-device radio communications, connectivity in data centers, information showers, okay, at 100 Gbps. These are the potential application of the millimeter wave and terahertz application. And also the positioning, the high precise positioning, that in the centimeter level positioning can also be possible by this millimeter wave and terahertz. Here is autonomous cars are shown here, drones, driver, robotics, all are using this millimeter wave and terahertz communication. Millimeter wave and terahertz imaging, that can body scanner using terahertz imaging to detect explosives. Okay, then millimeter wave imaging and communications for simultaneous localization and mapping, exploiting the scattering properties at millimeter wave. Now, in this figure, that wireless communication, that 100 gigabits per second, that is to 1 terabits per second wireless backhaul, that links over rooftops, that is established. So here range is quite high, quite big. Means, uh, whereas compared to the lower range, if we come then short range terahertz wireless connectivity in data centers, here it is shown. And also the on-chip and chip-to-chip terahertz communication links over the range of say 10 millimeter to 1 millimeter. And there is a transmitter, and this is the receiver. I already mentioned that precise positioning is also the one of the application for the millimeter wave and terahertz. Again, now interesting result will be shown that wireless at 140 gigahertz channel sounder and free space path loss at 28, 73 and 140 gigahertz. So here the measurements are shown, that path loss along the y-axis, x-axis tier separation. So path loss is increasing with the increase of distance, and at the same time among that increase path loss increases with the frequency. So 140 gigahertz we are getting the more path loss. Now here some interesting results are obtained by the changing the transmitter antenna and the receiver antenna, whether transmitter different combination of the directional antenna and the omnidirectional antenna. So this figure, that y-axis shows the received power and x-axis is the distance between the transmitter receiver. So in the y-axis the received power is in dBm, that is decibel milliwatt. It is shown that a set of graphs are there. So measurement takes place for three different frequencies: 28 gigahertz, 73 gigahertz, and 140 gigahertz. So higher frequency means the path loss will be more. As a result of that, received signal strength will be minimum for the 140 gigahertz, that is blue line. So this is the traditional what is expected for transmitter receiver omnidirectional antenna. That is blue, and the green line, that is 28 gigahertz. So received power is more than the higher frequency. So higher frequency 140 gigahertz is power level is minimum among these three. Where transmitter receiving omnidirectional antenna are used, but the case is different when the transmitter antenna is direct, transmitter and receiver antenna both are directional. Okay, in that case, that received power level is more in case of 140 gigahertz compared to 73 gigahertz and 28 gigahertz. So directional antenna with equal apertures have much less path loss at higher frequencies. So that can be exploited, and by this the range can be extended at beyond 100 gigahertz, 140 gigahertz. Another property, that penetration loss are different for different frequency and the depending on the material. So as you increase the frequency, then the penetration loss will be more. and that depends on the material used and the thickness also. So around 28 gigahertz, the penetration loss is around 3.6 to 6.8 dB, whereas 140 gigahertz, the penetration loss is 8 to 16 dB and depends on the material. Now, let me talk about the specifications of the 5G and 6G. So, let me highlight the important thing that data rate for the 5G targeted is 1 to 10 Gbps, whereas 6G is 100 Gbps to 1 Tbps, 100 gigabits per second to 1 terabits per second. So, huge data rate is required for the 6G, and so that can be possible by using the upper millimeter wave, that is the terahertz band, and reliability is 5G 99.9%, whereas the 6G the reliability is 99.999%, and connectivity is 1 million devices per kilometer square, whereas 6G is high density of the devices. So, let me quickly go through this 6G communication. There is the standard for the 6G, that is IMT 2030 ITU proposed, and immersive communication that uses the technology like virtual reality, augmented reality, and holography to create a sense of presence or being there for remote interactions. So the impact of technologies are that everything becomes connected, everything becomes software based, everything generates data, everything can be automated, everything needs to be secured. And that is the here shown the mobile broadband users are with the year, and that is shown this plot that huge traffic are there. So in order to fulfill the high data, high traffic, the 6G is also essential. So 6G architectural vision, that is connected intelligent network, then integration of AI and ML. So 6G AR interface and network designs will use AI ML to automatic system operation and administration. I'm not going into the details of that. So high reliability and low latency is has an important application in the e-health, where the reliability and the ultra low latency is very much important. This is the healthcare network architecture within 6G. So edge computing, AI, ML technologies are there, and then the millimeter wave, terahertz, physical layer, big data. So healthcare network architecture for 6G is shown here. And then next is the unmanned aerial vehicle. UAV has the many applications. So cellular network, that base station provides the coverage, but where coverage is not there, UAV, sometimes UAV is deployed that can act as the base station, and that provide the communication connectivity to the users. So here in this figure, UAV network architecture and use case in future 6G communication, that is home to hospital service. Here is the vehicular networks. Here end user devices. Here the smart city, low altitude UAV networks. So UAVs are low altitude UAV and the high altitude UAVs are there. So depending on the requirement, depending on the application, low altitude UAV will be used or high altitude UAV will be used. I am going through this, so let me skip this. I think connected autonomous vehicles are there. So sensing, communication, computation, positioning are there. The vehicular network or roadside units are there. They are connected. Vehicles are communicating, exchanging information with the roadside unit, and CAV requirements are extremely low latency, ultra high reliability, massive connectivity, and high throughput. And these are possible through terahertz, millimeter wave, and by employing edge computing, AI/ML. So now let me move on to the next topic, UAV-based wireless communication. So how many participants are there? Dr. Nanda, Dr. Ravi, are you there? Am I audible? Am I audible? Hello? Am I audible? Okay, okay. Thank you, Dr. Mathur. Okay, Dr. Nanda, thank you. Okay, next, let us
Yeah.
move on to the next topic, that UAV-based wireless communication. Uh,
Yes, sir. Please proceed.
Thank you. Now, UAV-based wireless communication. So, the importance of UAV-based wireless communication is that if, there are some terrestrial area where the communication coverage is not available. Okay, network is not available. So, difficult terrain where by employing the UAV we can provide the wireless communication. So, wireless communication in an urban environment is challenging due to the frequent obstructions and occlusions by building and other man-made obstacles. So, coverage and capacity limitations in cellular network. So, UAVs or drones can enhance communication reliability in such environment by acting as a relays or access point to assist the existing communication system. So, advantage of UAV in practical scenario, that UAV assisted communication systems promise to provide cost-effective wireless connectivity for devices without infrastructure coverage. And two types are there: high altitude platform and low altitude platform, and altitude between 200 meter to 6 kilometer. Compared to conventional terrestrial base station, there are many advantages of using UAV as flying base stations: easily deployable maneuverability, established line of sight communication links, and large coverage area. So now we shall talk about the channel characterization of UAV operated communication system in dynamic environment. And this work was published in the International Journal of Communication in the year 2020. Uh, so in the system model, that source is here at S, destination D. Two UAV we have deployed: UAV1, U1, and UAV2, that is U2. And so source to UAV1, that is the one link, that is RF link. User UAV1 to UAV2, that is over a distance of L U1 U2, and that instead of RF link, that we have used the free space optical link, FSO link. And from U2 to destination we have used the RF link. So this is the RF FSO RF link. By combining these, uh, we have studied that the symbol error rate, other performance metric, and the position or means, the link distance, elevation angle, how much will be the elevation angle. Okay, so ground to UAV model link, then the UAV to UAV link, and then UAV to ground link channel. So the distance are like that, say source to the projection of the UAV1, that is U1. So projection of U1, separation from projection of U1 to source is Lx, and separation between the destination and the projection of U2, that is Ly, small l suffix y. And the U1 and U2 are separated by this distance, L U1 U2. So two RF channel and one FSO link. So here we have assumed that the UAV are they are able to receive the RF signal and that signal, RF signal, will be processed into the optical, and then it will be able to send the optical signal. Similarly, this UAV2 will be able to receive the optical signal, and then it will be able to transmit the electric signal. So these are the assumptions we have made, and on the basis of this, that ground to UAV channel estimation model we have studied, we have done, and I'm not going into the details of the mathematics. So the channel ground to UAV channel estimation model, where the received signal symbol has been obtained, then the probability density function are calculated. Then the UAV to UAV channel estimation model we have analyzed, and the received symbol at U2, U1 is transmitted, so received symbol at U2 is derived. Then the atmospheric, because the free space optical link that is disturbed by the atmospheric turbulence, so that is taken care, and we have considered the moderate turbulence as well as the severe turbulence. And then we have modeled the UAV to UAV channel estimation model, and then instantaneous SNR is calculated at U2, and the average electrical SNR calculated, and then UAV to ground channel estimation model is used, received symbol YD at the destination is measured, is calculated, and then the instantaneous signal to noise ratio received at D destination is formulated by this, and then outage probability analysis has been studied, that if the instantaneous SNR falls below a certain threshold level of SNR, that is gamma TH, then outage takes place, and when the communication protocol is configured as decode and forward relaying mode, the equivalent SNR at the receiver can be expressed this, and the outage probability of the overall system has been obtained as this kind of expression. And also the symbol error rate for the MRF phase shift key MPSK has been obtained, has been used, and then the symbol error rate is derived. And then the optimal altitude analysis has also been done, and then the numerical results are done by MATLAB simulation, Monte Carlo simulation in MATLAB. So the moderate turbulence is considered for Cn square equal to 3 into 10 minus 14 meter to the minus 2 by 3, and Cn square equal to this value for strong turbulence. Means strong turbulence means the optical link will be disturbed more. Free space optical distance is 7 kilometer. That is the distance between UAV1 and UAV2 is 7 kilometers considered. And environment parameters are considered these, and the other parameters are shown here, and for these the results are like that. Here the optimal elevation angle versus the ly. So this plot y-axis is the optimal elevation angle, and this is ly is the distance between the destination and the projection of the UV2, that is ly. So the three sets of results are obtained when the projection distance from the UV1 to source is equal to the distance from destination to the projection of UV2, and in that case it is found that this green color curve, optimal elevation angle, and optimal elevation angle is when 500 meter value, then it is 75 around to around 60 to 75 degree elevation angle. Elevation angle means that in which direction the source will send the information to the UAV1, and in this optimal elevation angle is decreasing with the increase of ly. Then the outage probability is plotted for the different parameter out. This is with respect to the other parameters. So we have considered Lx and Ly, both are equal to 1500 meter. So and So two set of graphs are there, 1500 meter, Lx equal to Ly, and Lx equal to Ly equal to 2500 meter. And for the threshold value of gamma is 10 to the minus 5 is considered, and two set of turbulence, strong turbulence and moderate turbulence. So it is from our intuition that turbulence is more, then the outage probability is low for higher SNR, whereas low moderate turbulence, for lower value of SNR, outage probability is minimum. Lower outage probability is achieved. Similarly, the symbol error rate is for BPSK and QPSK are shown for the strong turbulence and the moderate turbulence. And this shows that the for UAV, how to establish a link from one source to destination where the direct link is not available, and instead of one UAV we have used two UAV for establishing the RF, then FSO, then RF link, and for establishing the link between the source and destination. Another work is also that is a UAV supported self-organized device-to-device network, and their maximization of instantaneous transmission rate in UAV supported self-organized device-to-device USDD. That is also presented in published in the year 2021. So here the system model is there. There are UAV. These are the UAV blue. That is the UAV are placed, and ground users are there. Many kind of users are there. So these are this is the block of the building. So there are different colors are shown. So these users are not, there is no direct, there are direct link and there are link through the UAV. So this user and this user, they are not, direct link is not available because of the building. But this user can send information through you to this UAV and from this UAV to here. So in this way the link is established through the UAV. But we have also considered direct link, and we have used the UAV assisted direct link between the device to device. So here this device and this device, they are connected directly without any UAV. They can communicate, they can exchange their information, they can, so this device can send information to this directly. So this is direct link. Similarly, this will be able to send here and from here to here. So some direct link devices are there, UV assisted link are there. There are some, and interference. This is the interference link by the brown dotted line. So here the this device will receive the interference signal from this UV. That's shown by this. So we shall consider that number of direct device to device pair, then the UV assisted device to device pair, and number of UV, and then the number of available channels for the UV. Then how to optimize the movement of the UAV so that the UAV association with the device will be maximum, and so that the instantaneous the transmission rate will be improved by this method. So this is the objective, and channel models are there. I think these are the channel models. There is already published paper, so anybody is interested can go through that paper. Uh, so that reinforcement learning is employed here, and the UAV can move in any direction out of it. So north, northwest, west, southwest, southeast, east, and northeast. And that state action space and reward formulation. So we have proposed a state action, reward state action search algorithm, and that algorithm is compared with other three existing algorithm. So we have compared our result with the, our algorithm is search algorithm, state action reward state action algorithm. is compared with the other three algorithm: random selection with fixed optimal relay deployment and RSFORD, then exhaustive search for relay assignment and channel allocation with fixed initial relay deployment, ESFIRD, then AOIV, alternative optimization for the individual variable. And for our results, the carrier frequency is considered 2 gigahertz, and that is the noise power spectral density is minus 174 dBm per hertz. UAV height is fixed at 500 meter, mm, uh, is considered. Then the other bandwidth is 1 megahertz is considered, and for different results are obtained. So this plot is shows that the total instantaneous transmission rate of UAV supported self-organized device-to-device network. So along the y-axis this and x-axis episodes, it is found that this result is considered where UAV assisted D2D pair is pairs is 10, number of direct D2D pairs 2, number of UAVs 5, available orthogonal channels are 7, transmit power of all devices and UAV are 10 milliwatt. And for this setup, we got the that our algorithm, Sarsha algorithm, gives the best result among the other compared to the other three: RSFORD, ESFIRD, AOIV. Similarly, the now same set of results have been other set of results are total instantaneous transmission rate of USSD2D network versus number of UAV that is considered for given set of parameters. Again, the number of direct D2D pairs are 2, number of UAV assisted pairs 10, available orthogonal channel 7, transmit power of all devices UAV is 10 milliwatt, and x-axis we are varying with the number of UAVs. Now, where we considered that number of available channel, orthogonal channel is 7. So, the performance after number of UAV 7 is not improved because the total available channel is 7. And again, the Sarsha gives the best performance, outperforms the others. Similarly, the total instantaneous transmission rate of USSD2D network for number of available orthogonal channels are shown here. Same kind of curve for different variations are showing here. Similarly, the total instantaneous transmission rate of USSD2D network or number of direct D2D pairs are shown here. So in this result, in this work, we have shown that by employing the UAV, the device-to-device connectivity can be enhanced. So we have and we have compared Sarsha algorithm with the other benchmark algorithm, and it is found that the superior performance in terms of throughput improves the total instantaneous transmission rate of the USSD2D network by 75%, 51%, 13% compared with RSFORD, ESFIRD, and AOIB schemes respectively. So I think let me stop here. Dr. Nanda, hello.
Yes, option.
I think
I yeah, I believe you can able to listen me.
so.
Yeah. So
Participants,
is there? Yeah, in the can you look at the right corner chart?
right corner,
So participants,
right corner star.
chart.
Yes.
Can you click there? So participants, if you have any query, you can write it on this chart. and professor will answer for the question. So if you have any queries, please write in this chat box. For the
So let me take one question that how adjacent channel interference and co-channel interference management done in phantom cell? Very good question has been asked by. As I have mentioned that in Vanita has asked the question. You know that we know that the adjacent channel interference, ACI, and co-channel interference that are present in the cellular system. So, how to tackle these interferences in phantom cell? So, so in the cellular system, the adjacent channel interference and co-channel interference. The co-channel interference, there is no way to overcome the co-channel interference in the cellular system. The system interference is there, but some designing the system has been designed in such a way that the effect of the interference will be minimized. So in the phantom cell, the split up of control and user panel, uh, as a result of that, macro cell uses the lower frequency band, whereas the under the macro cell, the phantom cell use the higher frequency band over small area. So both. So the question is in the phantom cell, small over the small area, higher frequency being used. Okay, so frequency reuse, the same set of frequency will be used, but because of the high frequency, so their coverage distance range will be not very high. So I think the effect of the interference will be not prominent like the cellular traditional system, or maybe the some other mechanisms are there. So next is the when millimeter waves blocked by human body, will it affect the human body parts? Yes, that is very good question from the, that is not only the millimeter wave signal, actually radio signal, the cellular system, cellular signal, that is also present everywhere, from the base station, from our mobile handset, always the radiation takes place. But mm, if the question is that it will affect our health if the exposure time is more. Okay. So, well, irrespective of the wavelength, irrespective of the frequency, but the exposure time, okay, that is important for the health issue of the human being. So that is another topic, that how radiation affects the human body or other animals or other living things, and that is the separate research issue, I think. So I think the researchers should take that action, that to conduct the research, that effect of the radiation from the mobile, maybe 5G, 4G, how it the affects the human being. So these are the good questions are asked. So anybody can take the issue and they can continue, they can start their research also.
any other query from any other participants, please type in the chat.
Okay, thank you. I think Dr. Vanita N has mentioned that it was useful session. Thank you, Dr. Vanita.
Any other participants, any other query?
Maybe the participants are less because today is the holiday weekend and the after lunch. So maybe, but anyway, the speaker has to speak, na? There is the freedom of the audience.
Now the schedule is there like that. Every day afternoon we are keeping this FDP, and
Okay.
on Saturday there is little bit extra session is
Yes.
there.
Yes.
So as there are no further questions, so I thank Professor for his wonderful talk of 2 sessions, continuous manner.
Yes.
Obviously, the information shared is very useful in this upcoming topic of 5G communication. Both the sessions were very much helpful for the participants of this FDP. So I am very much thankful to you, sir. Thank you.
Thank you. Thank you. Okay. Thank you very much. Let me stop. Let me leave. Thank you.
So participants, our next speaker for today, uh, Professor Vijayananda Patnaik, will join our session soon. Okay, so please wait for the next speaker to join.